Okay, so the last part of this chapter is about what's called rotational dynamics and inertia and looking at how things roll. All right, so as we talked about earlier, torque causes an angular acceleration. So a torque causes something to increase the rate that it spins. So if we look at the tangential acceleration is force divided by mass from Newton's second law. Angular acceleration is force divided by mass times the radius. So if we look at this diagram over here, we have centripetal acceleration, the tension force pulling in. We have the path of whatever this object is, the tangential force that causes the centripetal acceleration and causes the particle to change speed. That's what creates your torque, is you have a force applied out here. So it's not the tension that causes the torque, it's the force that's being pushed on it to cause an object to rotate. So torque is radius times the quantity of the force that you're applying to make it rotate. And we can find it by looking at angular acceleration is torque divided by mass times the radius squared. All right, so now if we look at a couple, like a net force, 3 different forces acting on this object that's rotating. Okay, for a rigid body rotating about a fixed axis, so like this, we can think of an object of consisting as multiple particles. So then you can calculate the torque on each particle, and then you can figure out the net torque. Okay, so because the particles rotate together, each of them have the same angular acceleration, because this object has to rotate at the same rate. Okay, so the torque for each particle is this quantity. Mass times the radius squared times the angular acceleration. Angular accelerations are constant, the masses vary, the radii vary. So the net torque is the sum of those. So we start off by doing net torques is just torque 1 plus torque 2 plus torque 3. Then we have torque 1, 2, and 3, etc. are found up here. But we can take out angular acceleration because angular acceleration is constant. So then you get angular acceleration is the sum of the mass of whatever particular point times its radius squared. So you end up with the angular acceleration is the sum of the mass times radii squared. So you add all of the mass times radius squared, multiply that by angular acceleration, and you get your net torque. So if you have forces applied at different points, you can look at the net torques if you know those forces, if you know the angular acceleration from up here. Now, the quantity of the sum mass times radius squared above is the proportionality constant between an angular acceleration and net torque. It's called an object's moment of inertia. Okay? So particle 1 is at radius 1 and has mass 1. And the force is exerted on a net torque about this rotation and cause it to have an angular acceleration. So the moment of inertia are these sums of your torques. Okay? The unit of moment of inertia is kilogram times meter squared. Think about it. Kilogram is unit of mass. Meters is your unit for radii. And the moment of inertia depends on the axes of rotation. So Newton's second law of rotation says that an object that experiences a net torque about an axis of rotation undergoes an angular acceleration. And I is the moment of inertia of that particular object. Make sure you understand this, that a net torque is the cause of angular acceleration. So again, looking at this moment of inertia thing, the moment of inertia is the rotational equivalent of mass. So the object's, if you have mass concentrated on the rim, larger moment of inertia, it's harder to get something rotating. Smaller moment of inertia, it's easier to get it rotating. That's why many of you found when you did the rotation activities that when you put all the mass in the middle, it spun faster because it was easier to get it moving because it had a smaller moment of inertia. Okay, again, the moment of inertia is the rotational equivalent of mass. It's it's more difficult to spin the merry-go-round when people sit farther apart. Kind of like if you think of a figure skater, when they start to spin, their arms are farther out, then they bring them in and they spin faster. So here's linear versus rotational. Again, like we did with the kinematics equations, we can do the same thing with Newton's laws. Force, mass, acceleration. The rotational equivalent of force is torque. The rotational equivalent of mass is your moment of inertia. And then you have accelerations, angular versus linear. And we can take the same equation, put it into the rotational relationship, and we get angular acceleration is net torque divided by the moment of inertia. All right, sample problem here. We're creating this weird little object here. It consists of 3 small heavy spheres attached by light 10-centimeter long rods, as shown to the right. The spheres have the masses as shown. What's the object's moment of inertia if it's rotated about an axis A and axis B? So axis A is here. So this thing is it's going to spin around this way. B is just going to rotate in a circle here. So we're going to use equation 7.21 to look at our moment of inertia. Is the mass times the radius squared of each of the points from where it pivots. Again, this expression R1, 2, and 3 are the distance of each particle from the axis of rotation. So that R is dependent on what's rotating. So particle 1 lies on both axes, so R is 0. Particle 2 lies 10 centimeters from both axes, so they're both 10. Particle 3 is different, because particle 3 lies 10 centimeters from this axis, since this is the one rotation, but it's not 10 centimeters from point B. We got to do some Pythagorean theorem to figure out where it lies. 10 squared plus 10 squared, the square root of 10 squared plus 10 squared is 14.1. So point 3 is 14.1 centimeters from axis point B. So we can make the R1s, R2, and R3 for axis A. We have that the moment of inertia is the sum of m times r squared, which is 0.025 kilograms times meter squared. For B, you add them up, it's 0.035 kilograms times meter squared. So if you look, B has a greater moment of inertia because point 3 is farther away from the axis point. Okay. Now, oftentimes what will happen is you're going to get equations for moments of inertia. Now you're not going to memorize these. These are not given to you on your formula sheets. However, if you need these on a test, you will be provided them. So again, the two determining factors for moment of inertia are mass, and if it's a plane surface, it's the length of the object from its pivot point. If it's any kind of circle, cylinder, or sphere, it's the radii. So make sure you look over those, jot them down if you want to, but again, you will be given those if you need them. The most common ones that are used often are the disks, the loops, and the spheres. Sometimes the planes of these things will be used, but a lot of what we've done in class so far has dealt with the rotation of spheres and disks. All right. So most of the mass of the hammer is in its head. So the hammer's moment of inertia is large when calculated about an axis, but it can be small when if the axis is not on the head itself. So you can look at different torques by holding at different spots of the hammer. All right, the next part is 7.6 about Newton's second law for rotation. Again, it's really rearranging the portion that we showed earlier, that angular acceleration is torque divided by moment of inertia. So we talk about something that rotates, like if somebody throws this giant stick called a caber. So this mass is almost 6 meters tall with a mass of 79 kilograms and landed on its end. It's tipped 25 degrees from the vertical and is starting to rotate. And we're going to figure out the angular acceleration of this caber piece. So this is our diagram here. So the torque acting on it is only due to its weight. So we know the angle here, which means we know this angle as well. Okay, so we know the length, we know the mass, and we know the angle. We're looking for angular acceleration. This is an important piece right here. There is no torque due to the force on the ground because it acts at the axis. So this is what's creating the torque, is the force basically pulling on the center of this caber. All right, so again, when we look at this, find our symbols and list the known information. There's two forces acting on the pole. The pole's weight, which acts on the center of gravity, and the force on the ground. The second force exerts no torque, so the force on the ground exerts no torque. So the torque is due only to gravity. So actually the torque is due to one component of gravity that's going perpendicular to the pole, which is why we call that your W sine theta. Right? So we'll model the pole as a uniform thin rod. Its center of gravity is at its center, a distance of the half of it. You can see from the figure that the perpendicular component of the weight is W sine theta, because we know this angle. So the torque due to gravity is L divided by 2, which is your R, times your force. Force times distance is torque. Well, your distance is half of your L, and the force is the sine of theta times your weight gets you that torque involved. So we can rearrange it and say mass times gravity times length divided by 2 times the sine of theta is your net torque on this pole. All right, so then the moment of inertia of a thin rod rotated on this axis is 1/3 ml squared. So we put it in here. So now we've got torque, we've got moment of inertia. We can simplify, put in numbers, and solve for it that the angular acceleration is 1 radian per second squared. Go through this problem a couple times, look it over, make sure you understand what you're doing, what it's saying. So the final result, the angular acceleration did not depend on the mass. Okay. So we have an airplane propeller. The engine in a small airplane is specified to have a torque of 500 Newton meters. This engine drives a 2 meter long, 40 kilogram single blade propeller. And on startup, how long does it take for each prop to reach 200 or 2,000 RPMs? So again, the prop can be modeled as a rod that rotates about its center. The engine exerts a torque on the propeller. Here's the situation right here. All right, so the moment of inertia of a rod rotating around its center is 1/12 mass times length squared. We know the mass. We know the length. We can find its moment of inertia. And we can find its angular acceleration because we know the torque. Torque is 500 Newton meters divided by the moment of inertia. Gets me an angular acceleration of 37.5 radians per second squared, which should be much more than the falling big Caber piece. And the time we need to reach it, that time we need to reach our final speed of 2,000 RPMs, which is 33 revolutions per second, which is 209 radians per second by problems we've done in class. If we know our initial velocity, our initial rotational speed, we know our final rotational speed, we know our acceleration, we can solve for time. So we assume that a constant angular acceleration, which is reasonable for air resistance and friction, will slow things down and make it more difficult. All right. A final thing that I need to show you here is a pulley, like we talked about in earlier units. If the pulley turns without a rope slipping on it, then the rope speed must exactly match the speed of the rim of the pulley. And the attached object must have the same speed and acceleration as the rope. So, the rim speed is angular speed times your radius. Just like we talked about angular or linear speed. The acceleration is angular acceleration times the radius, which means that your object's velocity and its acceleration must be the same. So if you know the radius, and you know how, like for example, you know how fast that object is accelerating up or down, we can find out its speed and its acceleration. Because the motion of the object must match the motion of the outside of the rim. Now, there's a couple sample problems on your Google form to try to figure this out. And because there are questions that show up like this on your AP exam. All right, the last part of this unit is on rolling motion. So rolling is a combination motion. So we have part of it's going in a straight line, part of it's spinning. And the figure above shows exactly one revolution for a wheel that rolls forward without any slipping. And in one revolution, the center moves forward by exactly one circumference. Think about this. We did this. We kind of did this in class with your lab. So we know that our tangential velocity is angular speed times your radius. And this is the rolling constraint, which is the link between translation and rotation for objects that roll without slipping. Translation means it just moves along. It's kind of slides, and rotation, it spins. So the point at the bottom of a wheel has a translational velocity and a rotational velocity in opposite directions. So the point at the bottom of a rolling object is instantaneously at rest. Hopefully that should kind of make sense to you. And so this is the idea behind rolling without slipping, is that momentarily it's not moving right there. Every other part is. Its linear velocity is canceled out by its rotational velocity, so momentarily it doesn't move. Okay, so we're going to do this. The diameter of your tire is 60 meters. You take a 60-mile trip at a speed of 40 miles per hour. What's your average tire's angular speed, and how many times did they revolve? So, angular speed is related to the speed of the wheel's center, okay? Because the wheel center of the wheel turns on the axis fixed to the car. The speed of the wheel center is the same as that of the car. So we convert it to meters per second. Once we know that angular speed We can find the number of times turned from the kinematics equations. So we have displacement is equal to angular speed times time. And we can find the time traveled from your angular speed is distance divided by time. So we know this. Angular speed is linear velocity divided by radius. Linear speed is 20 meters per second. That's 45 miles per hour into meters per second, divided by your radius of 0.3 meters. So you have an angular speed of 67 radians per second. Your trip time is 60 miles. Distance divided by speed is time. So 60 miles divided by 45 miles per hour is 1.33 hours. Multiplied by 3,600 seconds, you get 4,800 seconds. So the total angle through which the tire turns is angular velocity times time. We have our angular velocity, which is 67 radians per second. Our total time is 4,800 seconds. Is 3.2 times 10 to the 5th radians. So then we're going to divide that by 2 pi to get our number of rotations as 51,000 rotations. Very similar to what you did in class the other day. Okay. That is the end of Unit 7. Make sure you spend time answering the formative assessments. The formative assessment covers many sample questions that you'll see on the AP exam. And make sure you ask questions at the end of the form. We'll see you in class.